This is how space rockets are tested before launch. Welcome to SpaceX Zone. This channel brings you directly to space. So don't forget to like and subscribe for more out-of-space content. This is how space rockets are tested before launch. So hot that it can boil iron, so much noise that it can be heard up to 60 miles away, and so dangerous that it is plunged down by 1 million gallons of water every 3 minutes. Rocket testing, suffice to say, is a fairly intense process. But what exactly does a typical modern test facility fall short of? Join us today as we're all excited to take a look at how space rockets are tested. This month marks the 60th anniversary of Russian cosmonaut Yuri Alexeyevich Gagarin's first flight into space. So you'd be forgiven for thinking that rocketry was pretty well understood by now. Well, there really is a long way to go. From SpaceX's formidable Starship to NASA's moon-bound SLS Giant, there are giant new rockets out there than any attempted during the old-school space race. There are also different mission priorities these days, and even different fuel sources. Thus, the latest generation of rocket engines, whether they be Elon Musk's almighty Raptor or Uncle Sam's RS-25 from the shuttle program, need to put strictly through their paces on terra firma before trusting them with precious payloads. And of course, the delicate human being. Rocket tests fall into two broad categories: sea level ambient and altitude. This difference is important because at altitude, rockets produce more thrust in thin air and they must withstand less heat transfer. And these factors have major engineering implications. For sea level tests, the ambient atmospheric conditions around the test area work fine. But testing rockets at altitude is much more challenging, as technicians need to simulate conditions not in a blue sky, but on the ground where they can actually analyze them. For this, the rocket is placed in a sealed chamber where pressure is sucked up to about 0.16 psa with mechanical pumps, which is equivalent to the current conditions at about 100,000 feet above sea level. This sealed environment apparently creates problems of its own, so a process known as entering is initiated, whereby gaseous nitrogen or helium is fed into the chamber to prevent the explosive buildup of rocket exhaust material. Any kind of test, sea level or altitude, requires that brutal exhaust be directed somewhere, usually in the so-called flame bucket of the trench. The air pressure at sea level is way higher than it is above land. It funnels heat and energy in a direction where it can do no harm. A rocket's particular fuel source is a big determinant of how a rocket is oriented during the test. Liquid rocket engines are typically fired in a vertical position, as gravity is a part of the fuel intake process. Solid rocket engines can, alternatively, be fired horizontally, requiring a smaller and cheaper flame trench. However, it comes with its own set of issues, not the leasing noise, which we'll get to shortly. So, where exactly are these test grounds? Most modern rocket test facilities are located in the southern United States, in order to be near launch sites, which themselves are often closer to Earth's equator. Why are launch sites near the equator? The land around the equator moves at a speed of about 1,670 kilometers per hour, while half of the land towards the poles moves at a speed of only 1,180 kilometers per hour. This means launching from the equator enables the spacecraft to detonate already 500 kilometers per hour faster without any additional energy input. As such, SpaceX has a large rocket test facility in McGregor, Texas, which is handy for the company's Boca Chica launch and assembly site. But today, we are mostly NASA's John C. Stennis Space Center, Hancock County, Mississippi. It's where the new SLS rocket is being tried out in preparation for the first Artemis launch later this year, part of an ambitious program to put the first woman and next man on the moon over the next 3 years. Stennis has a good pedigree in this regard, as it was where the first and second stages of the Saturn V lunar landing rockets were tested in the 1960s. The spectacular historic A and B test stands are also registered as official National Historic Landmarks. From 1975 to 2009, Stennis also tested the main engines that powered the iconic NASA spacecraft's 135 missions. Indeed, the same RS-25 engines that powered the shuttle with some upgrades, naturally, are expected to send the SLS to the moon soon. The facility is so integral to American space lore that proud Stennis activists have said that If you want to go to the moon, you must first pass through Hancock County, Mississippi. Stennis is actually perfectly located for rocket testing. It is separated from major population centers on a 13,800-acre site surrounded by a buffer zone of 125,000 acres. Roadways and 7.5 miles of specially dug canals, lots of local water, a supportive local government, and an environment suitable for testing. At least not when hurricane season is in full swing. So what happens in the actual exam? During the recent SLS warm-up at Stennis, a variety of rocket systems were examined. Modal testing is a method of assessing the overall structural integrity of components, essentially by striking them with a finely calibrated mallet and measuring their resonance frequency. If the frequency is off in some way, this may suggest faulty welds, cracks, or other problems that could jeopardize the final mission. There is a so-called power-up process that must be followed to ensure that everything comes in correctly and in the correct order. The avionics, that is, the onboard mechanics and electronics, must all be tested, and fake curveballs must be thrown to reveal any unexpected vulnerabilities. An important aspect of rocket avionics is the gimbaling system, which orients the rocket boosters to maintain the overall trajectory. This system has its own hydraulics and must be thoroughly tested. There will be a series of simulated countdowns leading up to the so-called wet dress rehearsal, where propellants flow into the engine but do not ignite. To the SLS test facility at Stennis, approximately 700,000 gallons of propellant, that is 200,000 gallons of liquid oxygen and 500,000 gallons of liquid hydrogen, are piped from 6 floating barges. Its cost is around 114 tanker trucks. At the time of ignition, when the rocket finally fires, technicians need to keep track of some hair-raising physical changes in the rocket. With a temperature of minus 400 degrees Fahrenheit, thanks to that liquid fuel source, then while rising to a few thousand degrees Fahrenheit, the metal tank can grow and shrink by several inches. That monstrous exhaust would then jet into the flame chute, requiring 2 separate water suppression systems, both fed by a dedicated 66 million gallon reservoir. Every minute, 240,000 gallons of water are poured onto the chute to cool the engine exhaust during the test. In addition, about 92,000 gallons of water a minute are sprayed through a separate nozzle system to suppress noise. This noise suppression isn't just there to help with local property prices. This is to prevent all acoustic energy that would interfere with the finely calibrated test equipment or affect the physical performance of the rocket. Those giant plumes of white smoke emanating from the Stennis testing rig are actually steam from that huge torrent of much-needed cold water. To manage this aspect of its operations, Stennis has its own high-pressure industrial water facility and HPGF's high-pressure gas facility that helps pump gaseous nitrogen to the core state during testing. This prevents outside air from entering the test area during those all-important altitude tests. Along with the mechanical side, special software is also deployed during the test to control the avionics and simulate the various atmospheric conditions that the rocket may find itself subject to. Software is believed to have caused the catastrophic crash of the French rocket Ariane 5 in a mid-air crash in June 1996, so a lot is at stake here. All of these processes working in concert should aid in a test run that consumes 1.6 million pounds of thrust, or 2 million pounds at altitude, in the case of the SLS, as it produces about 2.6 million liters of propellant. Thrust is measured using a TMS, or thrust measurement system, which uses a series of load cells to calculate how much upward movement the thrust takes, taking into account the weight of the fuel. Once the rocket firing is complete, the real work begins. Some 1,400 sensors on the test site produce terabytes of data that technicians can view to make subtle refinements before a big launch. The impact of rocket testing, especially at Stennis, goes far beyond just firing payloads into space. The on-site Advanced Technology and Technology Transfer Branch were established by NASA to develop and share the knowledge gained at Stennis, enriching daily life for everyone, at least not the Mississippi economy. In 2018 alone, it is believed that Stennis' work benefited the local economy by $583 million. If you thought it was just a load of pyromaniacs in the Deep South exploding, what do you think? Is the rocket's ground test every bit as exciting as the lunar mission itself? Tell us in the comments. For now, thanks for watching and we see you at space.